Hey guys, so in a previous video, I really went over this notion of ds square. And ds square, we said, could describe the separation between locations. It would also be correct to say ds square describes the shape of a surface. Now, the way that this is going to come up is when we talk about surfaces, we could have a boring surface on which physics takes place, or we could have an exciting dynamic surface, as in cosmology and general relativity. And this is going to be very relevant for the notion of how our surfaces behave. So when we introduced the notion of the shapes of surfaces, we started with something that was just a flat sheet. So if I am constrained to only live and move around on a flat sheet, the shape of my flat sheet could be described like this. Now, what if I don't live on an infinitely large flat sheet? What if I live on a sphere? Well, a sphere is a different shape than a big flat sheet, so a sphere will have something different to describe the shape, a different equation to describe the shape of that sphere. And if instead I'm required to live on the surface of a donut, I have a different equation to describe the shape of the surface of a donut. Now, I could extend this idea to what if I don't live on a flat sheet? What if I live in a 3D volume? I could still think of a volume as being a type of surface that I live in, only now instead of having only two directions to walk around in, I have three directions to walk around in. So if I live in a 3D volume, then I could have a notion of this ds squared describing the universe that I live in. This describes the shape of the space that I live in. And if I want to incorporate a notion of time to allow things to happen, then I have a notion of four-dimensional space-time. And I could say the shape of 4D space-time is going to look something like this. Now, within this space-time, we have three spatial directions, x, y, and z, and we have a time direction I write as t. And we said in the previous video that we need time to be separations in time to be negative and separations in space to be positive to preserve the order of cause and effect. So this example here from a previous video where I talked about billiard balls rolling along a table is an example of, could be thought of as a picture of space-time. Here I only drew two space directions in, x and y, and then I have a time direction. There technically would be a third direction, z, but I can't draw a 4D picture on a computer screen, so I have to suppress one of the directions that things could evolve in or move in. Also, technically speaking, this space-time, the shape of this background on which things happen, this particular space-time I have written here describes an empty universe. So if the universe is completely empty, the background will look something like this. If the universe is not perfectly empty, the background won't quite look like this. It would look like something different. So when I talk about billiard balls rolling on a billiard table, well, that is not an empty universe. So technically this would not be perfectly 100% accurate, but it's a pretty good approximation for that scenario. So we could, as a thought experiment, just ask a fairly natural question. Is there a space-time that looks the same in every direction? So think about a universe. What would a universe that looks the same in every direction look like? So I think about it, and one universe that would look the same in every direction is a completely empty universe. So if there is nothing in the universe, it will look the same in every direction. Well, okay, that is one solution. Are there any other solutions to the question of, is there a possible shape of space-time? Is there a universe that looks the same in every direction? Let's suppose we have a universe with one particle. So I'll place a particle somewhere in the universe. I will call that the center. center is arbitrary. I'm allowed to set center to be anywhere I want, so I'll set it at the location of the particle. If I am viewing the universe from the location of that particle, the universe will look the same in every direction. So the space-time, the shape of the background universe, the shape of the stage that is space and time, when I have a single particle in the universe, is going to look something like this. So this is, M here is the mass of my particle, R is the distance from the particle. And again, like I said before, T is time, R is distance from the particle. Theta and phi could be thought of kind of like latitude and longitude. I spent a bit more time in a previous video talking about this with T, R, theta, phi. So this is our very inspiring result. Wow. Okay, so why is this result actually very compelling? We said before that you could think of ds square as the separation between locations in space-time. So not only locations in space, but locations in space and time. So ds square, the separation between nearby locations in space-time depends on which particle I place at the center. If I place one type of particle at the center, the separation will be something. But if I place a different type of particle down with a different mass, then I will have the separation between events in space-time to be something else. So the shape of space-time depends on the particle that exists in that space-time. So space and time are very intimately related with each other. So what are we going to do with this? Well, let's ask the question, what if I'm standing very close to the particle? So for the sake of argument, let's pretend the particle is pretty heavy, so it has a really large mass. Now, if I am close to the particle, then my distance from the particle is going to be small. So I could say, okay, this term r is going to be small. So r is small there. Now, if r is small, then 2m over r is going to be a number bigger than 1. Again, I don't know what this number is going to be. The important thing to take home is if r is very small, then 2m over r will be a number greater than 1. And you could just, if you don't want to follow along with the math, that is fine. Just pay attention to the next animation on the slide. If 2m over r is a number bigger than 1, then 1 minus that number is going to be a negative number. So this term in parentheses, 1 minus 2m over r, will be negative. Now, at this point, we could put that idea on the side. And remember from a previous lecture, we said that separations in time, we need to write as negative. So here's something that describes my separation in time. There's my negative sign. Separations in space should be written as positive. So here's a separation in space. Here's a spatial separation. Here's a spatial separation. All of these terms are positive. But when this 1 minus 2m over r term becomes negative, then what happens is this segment, I have a negative times a negative. Negative times negative gives me a positive number. I don't know what that positive number is going to be, but it really doesn't matter. The important thing is this term highlighted here becomes positive. So this term that was like a separation in time is now going to be more like a separation in space. And this term that is like a separation in space is going to become negative because I have 1 divided by a negative number. That gives me something that is ultimately negative. So a separation in time is going to behave kind of like a separation in space. And a separation in space is going to be kind of like a separation in time when I'm very close to that particle at the center. So let's explore what are going to be some consequences of this, or what could be an interpretation of this. So When I'm very close to the center, very close to the particle that I placed down, this spatial separation, this separation that was spatial is now behaving more like time. So think about, what does it mean to evolve through time? What does it mean to move through time? What does it mean to move through space? Well, when I'm moving through space, I can move back and forth at will, but moving through time, I can only move in one direction. I am moving towards midnight tonight. I cannot move towards 6 p.m. earlier today. 6 p.m. is in the past, midnight is in the future. I can only move towards the future. Now, this separation in space is going to behave more like a time, and this separation in time is going to behave more like a separation in space. So if I'm very close to the center, closer than a distance of 2m, the notion of distance from the center is now going to behave more like time. So right now, you're watching this video. You can move left, right, or up or down. You can move towards your computer screen or away from it, but you have no choice but to move forward in time. In this scenario that we're describing, when we are very close to this particle at the center, we can only move towards the center. So moving towards the center is mandatory. You're not allowed to get around that. So let's think about what we did here. We asked a very simple question. Is there a solution to Einstein's equations? Is there a universe? Is there a space-time that looks the same in every direction? And one answer we had is, let's place a particle in the universe and let's see what the universe looks like when you're looking out away from that particle. Now, we realize that the shape of space-time is affected by the properties of that particle. If we have a big mass or a small mass, that will matter. And if I find myself really, really close to the center, really close to that particle at the center, I can only move towards the particle at the center. Me trying to avoid reaching the particle at the center would be like me trying to avoid reaching midnight tonight. There's nowhere I could go. I can't do anything to avoid midnight tonight eventually reaching me. So I interpret this as, if I am closer than a distance of 2m from the center, I am currently inside a black hole. So if you're within this distance, you're inside a black hole, and it is only possible to move inward. It is only possible to move towards the center. Avoiding the center is like saying, I want to avoid 5 minutes from now. There's no way I could do that. The center is necessarily going to be in my future. So from this point of view, I could kind of think of a black hole as the collection of all events, the collection of all locations in space and time where the center of the black hole is in my future. Now, everything we said about a black hole in previous lectures is true. A black hole is so massive, light can't escape its gravitational pull. To escape a black hole, you have to move faster than light. Those descriptions are still true and valid. But in my opinion, this is a more fundamental description of what a black hole is. A black hole is just all the locations in space and time where the center of the black hole is in your future. And avoiding the center of the black hole is just as fruitless as trying to avoid 5 minutes from now. Now, in this lecture, I want to say before I run out of time for a YouTube recording, not every particle is a black hole. So a black hole is the mass of the black hole is at a point at the center. There are particles themselves could sometimes be thought as being spread out, and if a particle is spread out enough, it won't really be a black hole. There are reasons for that. So particles are not black holes, but black holes do behave like this. And I just brought up the notion of a particle at the center just to simplify some of this explanation.